So recall from our flipped class video that we were looking at velocity, and we knew if velocity is constant, say v of t is just some value v, then the distance traveled on some time interval, say from 0 to t, is just distance equals velocity times time. And that's something we've known for quite some time. And we saw another way to look at this was if we were to graph this. So if this is my t variable, say this is y, then we saw if we graph this velocity function, so this would be like y is equal to v of t here, and this is up at our height v, and we go over to our value t here. Notice the distance traveled was v times t, which is exactly the area below this. So it's also given by that area. So that was nice and easy if the velocity was constant. But then we looked at what if the velocity is not constant. So suppose we had some velocity function that looks like this. Let's say going like this. Let's say our t is right here now. Well, what we saw was we could break this up, and on each interval, and break this up into some intervals here. And we don't know how to calculate the velocity of the distance traveled with a non-constant velocity, but we could approximate our function with these little nice step functions. So you can see these steps here, they're not equal to the velocity, but they're an approximation to it. So if we call the steps here, if these steps are, say, f of t, then v of t is approximately f of t. And we saw the more steps we use, the better the approximation. And for each of these steps, the velocity or the distance traveled for the step functions, so the distance traveled is approximately the distance of step function velocities, which was, in this case, if we said this was, say, 0, and this was t1, t2, t3, t4, t5, and t6, the way we set this up, this would be the area of this rectangle, which is v of t1, and then say the width of the rectangles is delta t, plus v of t2 delta t, plus v of t3 delta t, up to v of t6 delta t. And we saw we could write this in summation notation. And so the more rectangles, the better we got. So we also saw that the distance traveled, well, this would be the limit as the rectangles get more numerous, which would be the limit as n goes to infinity of, say we make this sum again, but now we go out to n. And this is exactly turned out to be, if we looked at when we filled this in, it was the area under the curve y equals v of t. So we saw all of that except for the limit part in the flipped class video. So now let's go ahead and look at a different example. So we want to see that this notion of these Riemann sums here, remember this, we could also write this as this was R6 because we were using the right Riemann sums, and this would be Rn. So we want to know that these Riemann sums are useful for things other than velocity. So let's suppose have a solid pipe of length, say L, and radius R. So just something like this. Okay, and so the radius here is little r, and this length here is L. So if the density of the pipe is a constant, say rho, then the mass of the pipe is just the density times the volume, which in this case is rho pi r squared L. So just like we saw with when we were calculating distance, with the velocity was constant, then it was easy to calculate. Same thing here. If the density is constant, then this is easy to calculate. But let's suppose the density isn't constant and it changes as we go down the length. So if we say like here to here is x, we'll change that value. Let's suppose the density changes as x changes. So one end of the pipe could be more dense than the other end, or maybe the center is more dense than out at the end points. But it doesn't change radially, it only changes in terms of the length. Okay, so right here, say, this would have density rho x now. So we'll say this function is rho x. So now we don't have a nice formula for this because the density isn't constant, so I can't just multiply the density times the volume because it's changing at different spots. So what we'll do is we'll approximate this. So the most naive approximation could be, let's just assume whatever it is at the left endpoint is the density the whole way. So if we assume rho x is approximately rho 0, then we would say the mass is approximately rho 0 pi r squared L. We could also say, we could also assume it's the density at the other end. So maybe it's more like rho L. And then we would get the mass was approximately rho L pi r squared L. Or we could do this at any point at all in the interval. But if the density is changing from one end to the other, that's not really going to be a great approximation. So maybe what we do is we break up the lengths. So what if okay, so this idea of breaking things into pieces is really important. So let's think about what we're doing here. So let's suppose we just broke it into two pieces. So say this is a L over 2. So then we could assume that the mass is approximately, well, we could say we could say that this one here all has rho 0 approximately, and then say this one maybe is rho L over 2 for density. And if the density is changing, this is going to be a little bit better approximation, because say the density is really low at the left end and really high at the right end, at least we're getting something somewhat closer. And so now the volume of this part is still pi r squared, but now the length of this is L over 2 instead. And then for the second piece of this, I have rho L over 2 pi r squared, and then the width is, or the length of it is still L over 2. And we can recognize this as the left-hand Riemann sum here, because we're taking two two sums and we're using the left edge points. We could also use the right edge points. So this would be r of 2. Okay, so let's do one more iteration of this. So instead of breaking it into 2 pieces, we could break it into 4 pieces. So notice this is L over 4, L over 2, 3L over 4. And so again, we could approximate this with the left-hand sum. So this L is not the same as the L for the length. And this would be m of 0 pi r squared. And now the width of these is L over 4. Oh, this should be rows, not m's. All right, so notice those L over 4s are coming because we're breaking this length L up into 4 pieces. And we can also say it's approximately the right-hand sum with 4. So this would start at row L over 4 because that's the right edge of our interval. And so each time we do this, we should be getting a bit of a better approximation because the smaller the length of the pipe we're looking at, the more closely the density will be approximated by a constant. So instead of using 4, and I don't want to just keep going up and go to 8 or 16 or something like that, let's just go to n pieces. So we're just going to break this up into a bunch of pieces. So now the width of one of these will be, remember, so if we think of these as delta L's, so each one of these is width L over n. So this one would be at 0, L over n, 2L over n, all the way down to n minus 1, L over n, and then L, which is nL over n. So we break up into all of those pieces. And so now our mass, if we use n pieces, well, if we use a left Riemann sum with n pieces, remember this is the sum. Well, let's write it out without the summation. First, we're still getting used to that notation. So this would be row 0 pi r squared, and then the width of my rectangle, or width of my length of my piece of pipe is L over n. And then we go all the way, and this is the last one we use. So we'll do dot, 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 row. This will be n minus 1 L over n pi r squared L over n. And then we do want to write this one in summation notation. So it starts at 0. And notice we're going row. And then each time, this should be a 2. Oh, wait, no, that's right. That was just L over n. So this, notice we start with 0 times L over n, 1 times L over n, 2 times L over n, all the way up. So this is I L over n, and I have pi squared times L over n. And similarly, we could do the right Riemann sum. In this case, we'll just write this out. So now we start with the 1 and go up to n of row I L over n, pi r squared L over n. And we can see we keep getting better and better approximations the more pieces we break this up into. So the more pieces we slice the pipe into, the better our approximation. So the more and more pieces I use, the better my approximation. So what if we just let n go to infinity? That would give me an exact answer then. So I could say the limit as n goes to infinity of ln is actually my mass. So this would be the limit as n goes to infinity of this summation here. And same thing, we get the same answer if we use the right Riemann sum. So all we're doing here is we're just letting there be more and more of those pieces of the pipe. And so the more and more pieces, the better and better our approximation is until we get the exact value. So this thing here, and these things, let's just put them together, they're equal because they're both the mass, and these are what we call this a definite integral. So before you take the limit, they're Riemann sums. After you take the limit, they're a definite integral. And our notation for this, so we don't have to write out this limit with the Riemann sums every time, is we write the interval that we're going over. So we're going from 0 to L is what we're breaking up. And then we look at our function. So this is our function here. So we'd say this is rho x, and I have that pi r squared. And then this part here, right, this was our delta L, so we'll just call that dx. And this is the limit. We could do these with little l's or something if we want to, but we'll think of them like this. And it doesn't matter which one you use here, left or right hand sum. We said they're both the same. And so this is just notation. Even if you've seen this in a calculus class before this one, we're still just using this as notation for now. We don't know how to evaluate this other than taking this sum and taking limits, which is quite a bit of work. Okay, so let's see a concrete example of this. So let's consider the pipe with r being 2 meters, L being 10 meters, and rho of x being 3x plus 1 kilograms per meter cubed. So let's approximate the mass with L5 and R5. So this, we can get actual numbers out of this now. So notice the width, our delta x here, should be the length, which is 10 minus 0 over the number, which is 5. So each one should be width 2. So if we think of what we're doing in terms of the pipe here, we start at 0 and we go to 2, 4, 6, 8, and then 10. So those are our pieces we're breaking it up in. So the first one, the left sum with 5 subdivisions, this is the sum from I equals 0 to n minus 1. So in this case it will be 4. And we saw before this is rho of I L, which is 10, over n, which is 5. Or we can just, let's think of it this way. And then pi r squared, but in this case we know what r is. R is equal to 2, so 4 pi. And then my delta x is 2. So now if we write this out, this is rho of 0 times 8 pi plus rho of 2 times 8 pi plus rho of 4 times 8 pi plus rho of 6 times 8 pi plus rho of 8 times 8 pi. And now we can just fill these in. So 8 pi factors out of this whole thing. And remember, our row is 3x plus 1. So this is 3 times 0 plus 1 plus 3 times 2 plus 1 plus 3 times 4 plus 1 plus 3 times 6 plus 1 plus 3 times 8 plus 1. So this is 8 pi. And then if we evaluate this, it's 1 plus 7 plus 13 plus 19 plus 25. And this is 520 pi. And then the units here are kilograms. Okay, and then we can do the same thing with the right-hand sum. So now we're going to start our sum at 1 and go out to 5, because that's the number of subdivisions. And this is going to be rho I 10 over 5 pi times 4 times 2. So again, so now this is going to be, factor that 8 pi out. And then I've got row of 2 plus row of 4 plus row of 6 plus row of 8 plus row of 10. And we just calculated most of these. So row of 2 is 7, 13, 19, 25. And then the last one is going to be 31. So this is 760 pi kilograms. So we see using 5 subdivisions here isn't great. We're off by quite a few kilograms for what this could possibly be, but the more subdivisions we use, the better our approximation would be. So the next example we'll consider is probably the one you're familiar with if you've ever seen integration before. So we're going to consider area under a curve. So let's consider y equals f of x on some interval ab with f of x always bigger than or equal to 0 on AB. So always above the x-axis. So our picture for this example looks something like this. So say this is A, this is B, and my function might look something like this. So the question we're going to want to solve for this is we're going to want to find the area here. So we look at this, and we're trying to find this area. Okay, and we need, we're making this be above the x-axis, so area actually makes sense here. We'll talk about what happens if the function isn't always above the x-axis in a bit. So let's consider this problem then. So we could just use, so let's use rectangles to do this because we've seen we know how to calculate area of rectangles. We'll see later we can actually use other shapes too. We could use trapezoids, for instance, but we're going to stick with rectangles to start with. So again, we could use just one rectangle. So I'm going to draw my function to be a little bit simpler here. So let's just say this is my function. And we're going from A to B still. So if we just use one rectangle, we could use one just touching at the left edge and approximate with this area. And so for this one, we would say area is approximately, well, we're using the left edge point, so the height would be f of a, and the width would be b minus a, the length of the interval. And notice this is a left-hand sum with one rectangle. We could also do this with touching the right-hand side, so in this case, we would go up to here, do a rectangle like this, and look at this area here. So this could also be approximated by f of b times b minus a. And note this is a right sum with one rectangle. And we could also, maybe let's add one more to this, just to get an idea of one more way to do this. So another common one to use that we'll spend more time talking about later is we could use the midpoint. So let me pick a different color for this. Choose this one. So we could use the midpoint here, and we see this is actually giving me a better approximation because it's an over approximation for some and an under approximation for some. So for this one, we'd say the area is approximately, and we use an m for this for midpoint. And so the formula for this, well, the midpoint here is b plus a over 2, or b minus a over 2, sorry. B plus a over 2 would be even further out. So this is f of b minus a over 2, and then the width is still b minus a. So again, we see this is an okay approximation, but if we use more rectangles, we'll get a better approximation. So what about with 4 rectangles? Well, in this case, what would my delta x, the width of the rectangles, be? Well, this is b minus a, the width of the entire interval, and then I want to divide it into 4 pieces. And so what we would see then is, let's draw a picture and set this up again. And now I want to break this up into 4 pieces. So if I use left endpoints, my rectangles will look like this. And so what would these be? Well, let's call this x0, x1, x2, x3, and x4. So x0 is equal to a. And now to get to x1, I was at x0, and I went a delta x over. So this is a plus b minus a over 4, but we might want to just write this to save a little notation as a plus delta x. What is x2? Well, I'm at x1 and I add a delta x to it. So this is a plus delta x plus delta x. So this is a plus 2 delta x. And we can continue then. X3 would be one more delta x. This is a plus 3 delta x. And then x4 is a plus 4 delta x. But notice this is a plus 4 times b minus a over 4, which is just b, which is what we would expect. So then if we want to do the left-hand sum here, so L4, this would be f of a delta x plus f of a plus delta x plus a of f of a plus 2 delta x plus f of a plus 3 delta x. But we can also write this is f of x0 delta x plus f of x1 delta x and if we want to write this in summation notation, I start at 0 and go out to 3, which we could also write or if we want to include everything in there, like this. And similarly, we could write the right-hand sum. This would be the sum from I equals 1 to 4, because we want to use the right endpoints, of f of xi delta x. So maybe take a second to pause the video maybe and go ahead and make sure you understand where that came from. And now if we wanted to do the midpoint, this is a little bit more complicated. So for the midpoint, so this works really well and is better. You have to use less rectangles to get a better approximation, but writing out the formula by hand isn't quite as easy. So each interval is b minus a over 4 in width. And so when we're doing the midpoint, what this would look like well, we break this up into 4 pieces again. But now, instead of looking at those pieces, we want the midpoints. We would want to come to here and look at a rectangle like this. And you can see this does, even just looking at it, you can see this gives a better approximation because we get some over and some under. So it should just be a better approximation. But now we need to figure out what these points are. So if this is, say, this point here, let's call this x1 this time, x2, x3, and x4. Well, x1 is a, but then we've gone half of the distance over, so this is 1/2 b minus a over 4. So a plus b minus a over 8. And now we go a full b minus a over 4 to get to the next one. So x2 is a plus b minus 8 over a plus 1 interval width to go over. So if we simplify this, I get b minus a over 8 plus 2 b minus a over 8. So this is a plus 3 b minus a over 8. And so on. So if we want to do further ones, we're going to add another b minus. So I would have, this would be this one I just have, plus another interval width to get over. And then you can imagine the x4 is going to be a plus 7 b minus a over 8. So you can see they're more complicated to get than the actual left and right hand sums. So in this case, we would be summing from I equals 1 to 4. And my values that I'm evaluating this at, we're going up with odd values here. So this is a plus, maybe let's write it out with just without summation notation for this one. It'll be a little bit easier. So f of a plus b minus a over 8. And then the width is still b minus a over 4 plus f of a plus 3 b minus a over 8 b minus a over 4 plus f of a plus 5 b minus a over 8 b minus a over 4 plus f of a plus 7 b minus a over 8 b minus a over 4. So in future sections, we'll give formulas for the general midpoint sum. But for now, that's what it is for this one. So let's maybe, as we did before, let's work out a concrete example with some numbers. So let's let y be x squared, a be equal to 0, b be equal to 3. And let's find L3, R3, and M3. Okay, so our interval here is from 0 to 3, so our delta x we want to use 3, so this is 3 minus 0 over 3. So our delta x is 1. So if we think of breaking this interval from 0 to 3 up, I would go 1, 2, and 3. So my left-hand sum is going to be f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. So this is 0 squared plus 1 squared plus 2 squared, which is 5. So that's one estimate for our area. R of 3 is f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1. So this is 1 squared plus 2 squared plus 3 squared. So this is 14. And now for my midpoint, well, if we think of what we have up here, we're going to want to hit the middle of these. So I want here at 1/2, here at 3/2, and here at 5/2. So my midpoint is f of 1/2. Now the interval is still width 1. F of 3/2, width 1. F of 5/2, width 1. So this is 1/4 plus 9/4 plus 25/4, which is 35/4. So that gives us a nice concrete example of this. So now let's think of our general formulas. So that's the end of that example. Let's go back to our general setup of what we're doing. So for y equals f of x on AB with f of x bigger than or equal to 0 on AB. So if we want, what about ln and Rn? So for a general n, well, delta x is easy to find. This is b minus a over n. It's like we've been doing. And then we're going to break our interval up into n pieces. So x0, x1, x2, and so on. And this will be xn and xn minus 1 before it, and then all those in the middle. So x0 is going to be a. x1 is a plus delta x. x2, now we go another delta x, so 2 delta x, and so on. So in general, it's a plus j delta x for the jth one. So that means my left-hand sum with n subdivisions, we start at the left edge, and we go to the left edge of the last one, which is the n minus 1 term. So this is f of xi delta x, which we can also write. It's your choice which way you want to write this. If you write it with the xj's, you do need to specify what the xj's are, though. So this is a plus I b minus a over n times b minus a over n. So the second form there gives everything explicitly, whereas the first one you have to write out what xi and delta x are separately somewhere, but we figured that out above, so that's fine. And for this one, we start at the right edge points. We start at 1 and end at n. Okay. And just like before, we can see if we take more and more of these rectangles, we get a better approximation. So the exact area is going to be the limit as n goes to infinity of, say, ln or Rn. Either one is fine. They come out to be the same thing in the limit. So again, this limit here is our definite integral, and so our notation, just like before, is the integral, and now we're going from a to b as our interval, and our function here is f of x. And then we put the dx there, and so this is the limit as n goes to infinity. And I'll just write it with the left-hand sum. Right-hand sum is fine as well. Thanks. So that's how we do this, is find the area if the function's positive. So just for kind of setting things up for what happens overall, suppose I have a function that looks like this. And I want to go, say, from A to B here. And so I know to calculate this area here, this area, our shorthand from this, if we call this, say, C, is integral from A to C of f of x dx. And this is the area. So what would happen if I wanted to approximate what's going on for the second part here? Well, I could still use rectangles here. And this might make sense because if you're calculating, say, velocity, you might be going in one direction and then turning around and going in the other direction. So we want to say area is always positive. So if I look at this and I use those rectangles and I look from C to B of f of x dx, this is negative the area. So this is going to be a negative number. It's negative the area if you made that, think of this as a positive number here. So if you're just thinking of this in the plane, what is the area of that orange part? Well, it's some positive number here. So this shorthand is just going to give me the negative of that. And so we could see if I did the whole integral here, this would be the first one. So you take the first from A to C, f of x dx. So break all that part up into rectangles. And then you can go from C to B with the rest of the rectangles. Okay, so we're going to do one more example with economics to finish this section. So suppose we're going to look at deposits into a bank now and interest. So if I gave you $365 at the end of the year, say on the last day of December, you have $365. If I gave you $1 a day, all year you have $365. It wouldn't make any difference towards the end of the year. However, it does make a difference if you're going to do something like invest the money. So let's recall our formula for present and future value of an interest. So let's let R be our interest rate. And let's suppose we compound the interest continuously. Now remember, if you have a bank account, you know this isn't how it's done. It's usually done monthly. But it turns out that compounding continuously is a pretty good approximation, and the formulas work out much better. So our formula is the future value, which we'll write maybe as just f, is the present value, which we'll write as p, times e raised to the rt, where t is the time. So e to the rt. So for instance, if the interest rate R is equal to 4% and you deposit $100 after 1 year, your future value would be 100 e to the 0.04. So it goes up a little bit, not much. Now what we're going to look at is the situation of what if we have a company So suppose we have Pepsi or Coke or something like that is our company. With that, you're not getting deposits like at the end of each day or at the end of a year or something like that. You're making money constantly. There's always money coming in from selling Pepsi or Coke products. So let's think about what this could be. So let's suppose we have some set amount of time t. And we have money coming in at a rate of, say, P of t dollars. And this, we can think of this as dollars per year, say, or dollars per day, or whatever you want to do. It's just a rate here. So we want to calculate how much money will we have, say, at time t. So for instance, if I'm going to value something, I might like to know how much money am I going to make off my product over t years. Another thing you might be interested in is if you're going to buy a company, that company is going to make money over the future time, but you want to know what is a fair price for now. So in that case, you'd want to calculate the present value of all of this money that's going to be coming in. So what we're going to do for this is kind of what we've been doing so far, since we know that if we have a fixed amount, so I know if I put some amount P here, or let's say F there since it's kind of a future value, I know I could calculate how much it is back here by using our formula above. But since the money's coming in all the time, I need to calculate it all the time. So what I'll do is I'll break this up into a bunch of pieces like we've been doing. And even though the amount of money coming in at any particular time changes, over a short interval, we can assume it's constant. So on a short time interval, we can assume P of t is approximately constant. So let's look at some time interval in the future. So let's just think of this. We'll do left and right hand sums in a minute, but for now, let's just pick some time t and say I have some little interval here, delta t width. And let's calculate the future and present value of that. So how much money do we make in that time? Well, let's call this, say, t0. Let's say P of t is approximately P of t0 on the interval t0 to t0 plus delta t. If that time period's small, the rate of money coming in is not going to change very much. So to think about how much we make in that, remember that P of t0, this is in dollars per year. So it's dollars per unit time. So to get a dollars amount, we want to multiply by a unit of time. So it should be P of t0 times the amount of time we have, which is delta t. So this is approximately the amount of money we make in the interval t0 to t0 plus delta t. And so now if we want the present value of this, well, we know present value is future value e to the minus rt. So just take this equation up here and solve for p. And we know our future value is P of t0 delta t. And how far is the time? Well, the time here is t0 that we're bringing it back. So this should be e to the minus r t0. And if we want the future value, well, that's present value e to the rt. So we can look at this. How far are we bringing it forward to get to the future at time t? Well, this is t minus t0 for the time. So the future value should be the amount of money we make during that time, e, and now it's a positive rt, but now it's t minus t0 because that's the amount of time we're moving forward. So that's how we would deal with a chunk of money over some small interval. So let's think about how we do the entire interval now. So we're going to break it up into pieces just like we have been doing. So let's break it up into n pieces. So delta t is going to be t minus 0 over n, so t over n. And let's call this t0, t1, t2, t3, and so on. So t0 is 0, t1 is 0 plus delta t, which is t over n, t2 is 0 plus 2 delta t, which is 2t over n, and so on. So general tj is 0 plus j delta t, which is j t over n. And now we want to just think about each one of these little intervals and bringing that back in time. So our present value, well, the first one is p of 0. I have my delta t, and then e to the minus r, and then my t0 here. So let's just write it as t0 for a minute. Maybe let's write the other part as t0, and then we'll fill these in. And then I have the first one, p of t1, delta t, that's the amount of money I have. And then I want to bring this back t1 in time. P of t2, delta t, e of minus r t2. And all the way up, and since we're doing the left-hand sum for this, we're using the left intervals, this is going to be p of t n minus 1, delta t, e to the minus r t n minus 1. And if we want to fill these, well, let's maybe write this as a summation. So this should be an approximate here. This goes 0 to n minus 1, p of tj, and then let's reorder it, e to the minus r tj delta t. And if we wanted to fill these things in, we could. So tj, remember we saw was just j t over n, e to the minus r, j t over n. And then if we wanted to put the delta t in, that's just t over n. And this is L sub n. And we could do the same thing with the right-hand sum. We'll leave that for you to figure out. So then the present value would be the limit as n goes to infinity of L sub n, which is the limit as n goes to infinity, sum from j equals 0 to n minus 1, p of tj, e to the minus r tj, delta t. And now if we want to write this as a definite integral, our interval is from 0 to t, and now this is our function, so we're going to have p of t, e to the minus rt, and then my delta t becomes a dt. Now, there's a couple of ways to do the future value. We could just move it all to the present value like this and then just use our formula for future value. But for practice, let's go ahead and break this up into pieces for the future value as well. So I have t1, t2, and so on. So we have basically the same setup as above because it's the same interval. But now let's go ahead and do our left-hand sum. So I start with p of t1, but remember to make this a future value, this becomes e to the r, and then it's big T minus t1. Oh, this should be t0 because we're using the left-hand sum. Plus p of t1, e, oh, I need a delta t in there too. Sorry about that. Delta t plus p of t1, e to the r, t minus t1 delta t, all the way to the last one. So in terms of a summation notation, so same type of thing, only we're moving it forward in time instead of backwards in time, so it makes it a little bit more complicated. And so we can see the future value then is this limit again, we could use the right-hand sum if we wanted to, that's just fine. And so in terms of our notation, we're going from 0 to capital T, This is our function, so wherever there's a tj, we replace it with t, and then replace the delta t with dt, and that gives us our formula. Okay, so let's see a concrete example of this with some actual numbers in it. Okay, so we have some new computer software we're releasing. The sales start out really high, but then they decrease exponentially as time goes on. So we're going to take our time measured in years. The sales are, we'll say S of t, which is 50 e to the minus t, thousands of dollars per year. So after 2 years, version 2.0 comes out and replaces version 1.0. So let's assume all income from sales is immediately invested in government bonds paying interest at 6% compounded continuously. Okay. Let's find the present and future, or let's estimate the present and future value of version 1.0. Okay, so first thing to notice is we're going for 2 years, so our big T is going to be equal to 2. So let's do a couple of estimates here. So let's start with n equals 4. So in this case, my delta T is 2 minus 0 over 4. So this is 1/2. So my Tj, T0 is going to be 0. T1 is 1/2. T2 is 1. T3 is 3/2. And T4 is 2. So my present value, which is approximately L of 4, this is P0 e to the minus r times 0 delta t plus P of 1/2 e to the minus r 1/2 delta t plus P to the 1 e to the minus r times 1 delta t plus P of 3/2 e to the minus r 3/2 delta t. And now we can put some of these things in. So let's leave our r's for the end. P of 0, remember our formula here is 50 e to the minus t. So this is 50 e to the minus 0, e to the minus 0, so that's just 1 delta t, plus 50 e to the minus 1/2 e to the minus r over 2 delta t, plus 50 e to the minus 1 e to the minus r delta t, plus 50 e to the minus 3/2 e to the minus 3/2 r delta t. And so now we can fill these things in. So this is 50, and then we just have our delta t, which is 1/2. And I have 50 e to the minus 1/2 e to the minus 0.06 over 2 times 1/2 plus 50 e to the minus 1 e to the minus 0.06 times 1/2 plus 50 e to the minus 3/2 e to the minus 3 times 0.06 over 2 times 1/2. And if we simplify that out, this is about 56.49, and this is thousands of dollars. And so we can do the same thing for the right-hand sum. For the present value, and R4 is equal to, just run through the same formula, it's going to be the same at the beginning, and then we take off the first term because we don't want the left edge, and then we add on one at the end. So I'm going to have 50 e to the minus 1/2 e to the minus 0.06 over 2 times 1/2 plus 50 e to the minus 1 e to the minus 0.06 times 1/2 plus 50 e to the minus 3/2 e to the minus 0.06 times 3/2 1/2 plus 50 e to the minus 2 e to the minus 0.06 times 2 times 1/2, and this is about 35.31 thousands of dollars. So that gives us our two approximations for our present value. Future value is going to be the same idea, just with the other formula. So this is going to be P0 e to the r, and now I have the t minus t0, so 2 minus this, delta t plus p of 1/2 e to the r, and I have 2 minus 1/2 delta t plus p of 3/2 e to the r, 2, or this should be with a 1, sorry, skipped one there, 1 p to the 3/2 e to the r, 2 minus 3/2 delta t. And we can just fill all of these in, and so this is 50, and then I have e to the 0, maybe let's just fill it all in. So this is 50 e to the minus 0, and then I have e to the 2r delta t plus 50 e to the minus 1/2 e to the 3/2 r delta t plus 50 e to the minus 1 e to the r delta t plus 50 e to the minus 3/2 e to the 1/2 r delta t. And then if we fill all of that in, this gives me about 60.29 thousands of dollars. And so we'll leave the right-hand sum. So let's work that out as an exercise. And so you can check that on your own. This should come out to be about 35.49 thousands of dollars. Now, one thing to note is we're only using 4 subdivisions, but these are huge differences. These are supposed to be estimating the same amount, and one of them gives me 60 and one of them gives me 35. So that's not so surprising because we're dealing with exponential functions. So left and right-hand sums are pretty bad with exponential functions. So suppose we did 1,000 intervals. And obviously we wouldn't want to do this by hand, but if I plug this into a computer, this is about 41.55, and the right-hand sum is about 41 0.46. So we can see these are much closer together. They're still not great, but we've used 1,000 rectangles. We'll see later using trapezoid rule or midpoint rule or something called Simpson's rule would give us a much better estimates much faster. So left and right hand sums generally require us to use a lot of rectangles to get reasonable approximations. And so if we use 1,000 for the future value, we get about 46.85, and the right-hand sum is approximately 46.75. So again, better, but not great. We'd like them with 1,000 rectangles to be almost equal. But it does show increasing the rectangles does make a drastic difference. And if you're using a computer, the difference between 4 rectangles and 1,000 isn't going to take much time. So we'll eventually see how to evaluate these integrals exactly so we can get exact numbers and we don't need the approximations. But one thing to keep in mind going forward with integrals is most of the integrals that you would encounter in the wild, like in real life, we don't have nice formulas for. So these approximations are very important to understand.